Anyways, but okay, so just to remind you what we were doing, so we defined for every code in the Hamming space, we defined this parameter, namely list decoding radius, which is maximum relative radius, such that for every ball of this radius, it does not contain more than L points. Okay, and so after some pain, we learned yesterday that oh yeah, of course, and what we are interested in, so the theorem that we're trying to prove is that tau L star of rate, that for any code of rate R, this tau L star is upper bounded by some function G1 of delta LP1 of R, where this is the linear programming bound. So delta LP1 of R is 1/2 minus root beta 1 minus beta, and okay, G1 of nu, I'll define it in a second. Sorry, I mean, okay, I can define it right now, but it's the following strange object. Okay, so, and these guys are IID, Bernoulli, nu. Okay, so
what did you write? Can you read it out to us? The expectation of?
Okay, so this is the expectation of the average radius of the following L+1 points. The first, so I didn't define what the average radius is, but it's a certain function. So, and the points are, this is all one dimension. So these points are 0 and L Bernoulli IID vectors, and expectation is over them. Sorry, these are not vectors again, 0, 1 values. So in particular, for example, for L equals 3, G1 of a, oh, this is for only for odd L greater than 3. This is the theorem. Right, and for L equals 3, G1 of nu, I mean, it's always a polynomial, so it's something like this. Just explicit. Okay, so what's the average radius? So the average radius, oh, first of all, what's the usual radius? The usual radius of any set is the minimum over all possible centers. Basically, it's the Chebyshev radius, right? So it's the smallest circumscribed sphere. So it's the minimum over y.
But these are a set of points on the real line. It's one-dimensional.
Yes.
The radius is the distance between the two divided by 2.
No, but this is Hamming space. So
It's some sort of majority.
it's a majority, yes.
Because I don't understand the setting. B1 up to B L are numbers.
0, 1 numbers, right. And you consider the Hamming distance. Okay, yeah, you can consider the Euclidean distance. Okay.
No, but I don't understand.
Oh, I see. Okay, so you see. Right. So I'll write it. So when you do the radius of circumscribed sphere, right? This is like you're saying if I have 2 points, for example, 0 and 1, I can put the center here. But no, this is forbidden because this point is not in my space.
I'm sorry.
Okay, let me write the definition and then you'll see. So it's so this is the definition of the radius of a set, right? And S is a subset of f2 to the n. Right. And the average radius, or the moment of inertia, is minimum over y. I mean, all these guys are in f2n. That's important. And here you just compute the average distance. Y.
But you define the radius of a set, and
Right.
what appears there is that a set? It looks to me like a vector.
Yeah, good point. This is a bad notation. Okay.
It's multi-set.
Right. It's a set with multiplicities.
The B's are 0, 1s.
Let's say.
So it's a multi-set. 0 appears 10 times, and 1 appears L minus 10 times.
Yeah, then if you just pick
Yes.
0, 1,
Yes. Right. Exactly.
Oh, okay, thank you.
So yeah. So this is abusive notation. I don't know. How do you denote ordered set? Is there?
Now I understand.
Okay. Okay. So then I'll just keep writing this. Just multiset.
Okay.
Right. So, okay. So, right. So, the way the bound looks. Oh, actually, in terms of this notation, the Plotkin radius is what? So this is the general trade-off: r versus tau, right? So the bounds are like this, and this point, tau L star at 0, is something like expected average radius of B1 up to BL plus 1, I think. And these are Bernoulli 1/2. So this is just what Blinovsky proved. So hopefully I'll get to the point where you will see why something like this should be true. Okay.
What do you call the Plotkin point?
Right. But this is just the usual Plotkin point for the original problem. Okay, so what we did yesterday, we learned that from Calais lineal there exists psi 0, and okay, it was very important that this psi 0 is between 1/2 root beta 1 minus beta. Beta is found from solving for a rate, solving this equation. With what property? Okay, so there is this psi 0 and code word in the code such that C plus sphere of radius psi 0 n intersected with the code contains greater than 2 to the n r prime code words. Right, so geometrically, so we started with some unknown code, and Calais lineal give us some code, some point in the code and a sphere such that there are exponentially many code words on that sphere. This is the first step in my reduction, right? So then I forget about everything else, and I'm just going to compute the coverage radius, the least decoding radius of this subset, this code point plus these exponentially many code words on the sphere. Okay. So let's call this guy, this intersection, right? This is C prime. Okay, so
1 minus h of beta is r?
I think it's h of beta actually. Yeah, I think yesterday I accidentally wrote 1 minus h of beta. Yeah. Okay, so for example, if just sort of we're going to be mostly interested in this regime, and so when rate is epsilon, then beta is root epsilon, and psi and this point is going to be 1/2 minus root epsilon. That's important. So this is sort of the parameters and the psi 0. And actually we will see that, okay, later we need to optimize because we don't know where this sphere is, right? We only have upper and lower bound. Sorry, we have upper bound. So we will need to take the worst bound, and the worst bound will always be on the boundary, right? So just to think about parameters, this is the interesting case, right? So my sphere is almost of the full radius minus root the rate. Okay, so then the next step, and that's what I hope to talk a little bit about today, is to solve this sub-problem, right? So now we are solving sub-problem. Okay, so given S psi 0 n, which is a Hamming sphere, right? Is there a question? Or? Okay, so then pack a maximum number of points such that the following, so usually we code for the minimum distance or for the least decoding radius, right? So here we code for some absolutely useless parameter, which I think never appeared anywhere, but so this is the metric of interest for us, for the code. It's the maximum radius such that ball intersected with C has less than L minus 1 points. And this ball, in addition, for all balls which intersect, which contain 0. So it's like you want to pack points such that you cannot include L of them in any ball which also includes a 0. You want to minimize this. Okay, so it's obvious that this radius can never, so this tau L is always greater than 1/2 psi 0, right? Just because if you want to include any point here and 0, your radius has to be half of this, right? And on the other hand, it's obvious that this tau L is smaller than psi 0, right? Because if you just put the center of the ball here, you include everything. Okay, so then we know two things about this trade-off already, right? So if we consider the maximum rate you can have is h of psi 0, right? The size of the sphere. And here we have these 2 points, and the question is, okay, so where does this rate hit 0? Right, so what's this point? And this is basically the main work. So this reduction is the same as Ashikman, Bargan, Litzen. So the main work was to establish this. Oh, actually, yes, well, yesterday I forgot to mention what's the term. I mean, when you think about it, there are many points that you can improve in this proof, in my opinion. But my main motivation was to show 0 slope. Why? Because one of the ABL authors, which showed 0 slope for list 2, they told me, I'm not going to say who, but they told me that they believe 100% that linear programming methods are unable to show 0 slope for any list size greater than 2. Why? Because basically linear programming methods are inherently point pairwise, and you need to consider triple-wise and quadruple-wise statistics to say anything meaningful about list size greater than 2. So that's so once I showed this 0 slope, I mean, I just wanted to show an example that it's actually possible. Okay, so right. Okay, so yeah, so the main proposition is the following. So for any code with huge size, tau L0 of C, so this weird metric, packing metric, is always upper bounded by G1 of psi 0. Okay, so so how are we going to prove this? Okay, so for that, let's first let me first do the following simple computation. So the proof is sort of warm up step 1. Let's consider the following different metric of the code. I will call it tau L bar, which is the average radius. Right, so this is going to be expectation of radius 0, C1 up to CL. Where these guys are taking uniformly C. Okay, so I mean, this is a different metric, right? Of course, the average such radius is always a lower bound, right? Tau L0 C is always greater than tau L bar 0 of C. So there is no upper bound like this, which I can state, but let's just still do it. Let's show that if this is my figure of merit, then this is the right Plotkin point. Okay, so how are we going to do it? So for that, I just need to okay, so when you compute the radius, right? So suppose I give you some number of vectors in the high-dimensional Hamming space. So on. So the important thing is that radius, the average radius, can be computed on a per column basis. Why? Because the only thing you care about is really, so basically the center is always the majority vote. Right? So the center of moment of inertia is always majority vote per column. Right? So you consider each column and compute the majority vote. Right? So, okay, so then again, this here you have basically two averagings, right? The averaging of a selection of a point, so you can interchange these two averages, and so this quantity is basically the following. So if you write down the code as 1 cross 2 to the nr, 2 to the nr matrix, right, of n, it's 1, 2 to the n here. So if you write this matrix, right, so and you look, so when you compute this expectation of this radius, what you should do is you should select a random subset of size L, right, random of size L, right, add a 0 here, and then compute the majority vote for this random subset, right, compute majority vote, and average over all such selections, right. So basically what I'm saying is that it's very easy to just verify that this expectation is always equal to the following thing. So just inequality, it's just exactly equal to sum over I from 1 to n of this G1. Oh yeah, and of course, so let's define the density of ones here to be lambda I, right? So then when you select a random subset of size L, right, basically because L is fixed and this number is growing, what you get, the statistics is exactly IAD Bernoulli, right, for these bits. This is some kind of selection with replacement, without replacement, right? So it's okay. So what you get is this function G1, which is exactly what we need, right? The average radius in the one-dimensional case, and lambda I is the density of ones in the ith column. Of ones in ith column. So this is just equality. There is no cheating here. Okay. Then you actually observe that luckily these G1 functions are concave. So then this is always upper bounded by n times G1 sum of lambda i's normalized by n. Okay, and right, so there was this all-zero vector which we put as an anchor for our radius computation. Right, and now just by seeing that, okay, this code C lies every row contains exactly psi 0 times n ones, right? This is just sort of averaging in two different ways, right? So this is exactly psi 0, right? So this is a okay. So right. So you can see that the average radius of arbitrary code is always upper bounded by what I claimed here. Okay. Now you can actually indeed, if you just do a random selection of 2 to the nr points uniformly in the sphere, you can easily see that the average over that random selection will actually hit this very easily. And basically what I'm saying is that this estimate is tight. I mean, you need to do some expurgation and then apply this bound. Okay, so this is achievable. Now the question is, how do we go? So we now know that this sort of we have an upper bound on a lower bound, right? So far it's a completely useless thing. So how do we guarantee? So how to now guarantee? L0 of C is also less than G1. Okay. So far let's just understand that this was a lemma, right? Simple computation. That the only thing we use is that this number of code words grows to infinity, right? That's the only approximation we used here to replace this selection with replacement to something without replacement. So now I need to tell you how actually Blinovsky proved this estimate, because so far I'm just following his strategy. He did exactly the same thing, and he was able to show that indeed average radius and maximal radius can be interchanged. So let me quote his result. Polyanskiy showed for every code, for every large code, there exists a subcode which is much smaller than C, but still, basically when I write this means as the size of this code goes to infinity, the size of his subcode also goes to infinity, with the astonishing property that the average radius is equal, well, approximately equal as n goes to infinity, right? Approximately equal to the maximal radius. Okay, so then I knew this result, right? So when I showed that, I mean,
For C.
oh yeah, sorry, this is for C prime, right? So basically every code contains what he called a symmetric subcode, namely the guy for whom average radius and maximal radius are exactly the same thing. So now the question is, okay, I knew this result, and this all, I mean, took me maybe, including Kalai lineal, maybe, I don't know, 1 day. And at this point I thought, okay, so this is a very simple computation, you know, you check it. So I thought, okay, now I just need to prove that the same thing holds for tau L0, for this weird anchored average radius, right? But actually it's not true for tau L0. For tau L0. Okay. Tau L0 versus tau L0. So here is a very simple counterexample. So so remember, this is our anchor, right? So 0 is always there, and so we put all the points here, right? And think of L huge, something like 10 million. Right? So, okay, so you have 0 and then lots and lots of points here. So then what's the average radius? If L is gigantic, right, and this, remember we are averaging, and then the contribution of 0 as if it doesn't exist, right? So then tau L is approximately 0, but the maximal radius is always at least half, right? So, so there's absolutely no hope in proving such a result. So here I need to admit to you that I've been lying everywhere here. Actually, this is not true. And what is true is that I need to replace this estimate by something else. So it's about 5 minutes. Okay, so I think, I mean, again, so my time planning is very bad because I hope to, so yeah, so okay, so what I could prove. So, the proof is the following. So every C, for every code on the sphere, there exists C prime, subset of C, and C prime, well, goes to infinity as C goes to infinity. With what property? Well, with the property that tau L0 of C prime is approximately equal to, not to the average, we know it cannot be true, right? But it's equal to the following interesting thing. It's maximum over J belonging from 0 to L of what? Of something which is very close to the average radius in spirit. First add 0 J times, and then you put the average over your L code words selected at random. Right, again, the subset of L code words is selected uniformly at random, right? Uniformly from C prime of choose L, right? Okay, so you can see that basically in this, what I do here is for each J, right? I mean, as I add more and more zeros here, I improve the contribution of 0, right? And that's why this counterexample basically disappears, because when, for example, when you add many j's here, the contribution of j becomes at least as much as the collective contribution of all those guys. Okay, so the proof is, yeah, I don't have time, but it's not terribly different from Blinovsky. I mean, I was surprised that I could do something like this. There's one extra trick I needed to use is, I think, yeah, so one thing I noticed is that by using minimax theorem, you can prove the following general property of the radius, that this radius is approximately equal. Okay, let's just take exactly math. It's equal to max over distribution p of radius bar of what? Of C1 up to CL, but when you compute the radius, you have a weighted contributions with weights P1 up to PL. So P is the distribution. This is not trivial, and this is actually not true the way I stated it, but plus minus 2 to the L. So the reason you never probably seen such a thing is because when people compute radius, they are very rarely interested in my regime, right? My regime is the dimension of my space is huge and the list is fixed, right? So that's why such approximation. Basically, this is minimax theorem here, and that's what allows me to, carry over expectations and so on. So this is what connects radius to expected radius. Plus, there is Ramsey symmetrization happening. Okay, so. Right, so this basically, this tells me that what I need to replace here is I need to put maximum over j of gj, where gj is exactly what I defined as expected radius in dimension 1, but with j zeros added. But actually, so when psi 0 is greater than 1/2 minus delta, so when it's very close to 1/2, and remember that's the regime of interest in low rate, right? It turns out that the maximum is always achieved. Maximum is achieved at j equals 1 when L is odd, and j is 0 when L is even. Okay, so this is the math explanation why my proof doesn't work for even, because G0 actually looks like this, and it achieves, so it hits 1/2 with 0 slope, but G1 has a constant slope here at 1/2. So that's why when you plug this thing in here, so for even L, you have to square this epsilon, so you get the constant slope, rate epsilon, and the bound is a epsilon. Right, but for odd, you have rate epsilon, and the bound is root epsilon. So that's what gives you the improvement. So this is a sort of a math explanation, but the high-level explanation why my proof works is the following. So you see, when you consider the sub-problem, it's as if you're doing list decoding, but with list size L minus 1, right? List size of 1 less. And when L is odd, so how does Plotkin point look like? So for list size 1 and 2, it's here. For list size 3 and 4, it's here. So there is this strange periodicity, which only happens in the binary case. And right, and so when you ask me to prove something for list size of 5, right, what my proof is effectively morally reduces to proving something about list size 4, right? And then we know that for list size 4, for small rates, you have a much better converse bound, right? But when you ask me to prove it for L equals 6, I reduce to L equals 5. And here, of course, they are we have very comparable bounds. So roughly speaking, that's the reason. So, thanks.
Any quick questions? But the fact that the maximum is achieved for j equal to 0, does it mean that here you actually add only 1 0 in the list?
0 zeros.
So 0 zeros in the list?
Mm-hmm.
So that the previous statement would be actually true?
Okay, that's, you mean which statement? This thing? It basically means that, so when you have 0 zeros,
So you're not was adding the center to the statistic.
Okay, so you see, no, first of all, this has no longer any code words in it, right? So this is just evaluation of a function.
Yeah, but you're doing the averaging that you did there, more or less. Or?
Okay. Anyways, Marco, let's think about it later. But yeah, I remember I thought about it basically in you say that if I have 0 j's here, this is like tau L minus 1, right? So this is like L minus 1 packing of these guys. Yeah, I remember there is some connection, but I forgot in what sense now, since I did it a long time ago. So.
Okay, let's take other questions offline.
All right, yeah, and thanks again.